I suppose, is the fact that we didn't even know that we lived in a galaxy for up until just about 100 years ago. So while it was pretty obvious we lived next to something pretty bright and easy to study, it's actually not that easy to study in the case of our star, the sun. It's actually not that easy to study the Milky Way Galaxy because we can't see the forest for the trees and the dust. So we're going to come to that. It's really kind of an interesting story as to how we figured out that we do live in a galaxy. So here's what we see in the night sky. And this is the summer Milky Way. It's the brightest part of the Milky Way. And we weren't really sure what we were looking at. William Herschel, back in the 1700s, did use a telescope, and he could see that along here and here, you could see many more stars per square degree than you could see out here. And of course, that's obvious by eye as well. And he made the simple but not too unreasonable assumption that on average stars are about the same, and therefore seeing so many dim stars here, what you're really seeing is that stars that were probably something roughly like the sun, and they were just farther away. So he mapped out what he called the universe, but we now know to be the pancake-shaped thing, which is our galaxy. And then notice how along the middle here, you don't see so many stars, and of course he didn't see so many stars either. He wasn't sure what to make of that, but it does show up in his early maps of what he called the universe. Now, looking out nowhere near the Milky Way in the sky, in fact, you want to look at directions opposite the Milky Way, near the galactic poles, and since the 1700s, when we had telescopes good enough to see them, we saw these faint fuzzy blobs. And in fact, the better the telescopes got, the more of these fuzzy blobs we saw, to the point where, in fact, today there's more of those than there are stars. They're easier to find in terms of how many per square degree than there are actual stars. We didn't know what they were. They were dim, they were fuzzy, they were oblong. They had a central bright concentration, what we would now call a central bulge. So were they nearby solar systems, perhaps, that were still forming with the sun at the center, and that was causing the excess brightness? Or were they perhaps giant pancake systems of uncountable numbers of stars? In other words, if you take what Herschel saw and assume that it has an edge, and then go out many, many times further away than the edge, which was kind of mind-boggling back in those days. Now you're talking about millions and millions of light years. Then you could imagine that those faint fuzzy blobs could be entire systems just like our own. But it wasn't obvious what they were, and the debate over which of these two was correct kind of raged right up until the 1920s. So how did we finally figure that out? Henrietta Levitt is key. She was an astronomer at Harvard Observatory, and she worked in their Cape Town, South Africa observatory, where there's a great view of the nearest and largest, brightest, I should say, galaxy, as we now know, in the sky. And it's called the Large Magellanic Cloud, named after Ferdinand Magellan, who first saw them, the first European to see them. Obviously, native people in the southern hemisphere had seen them for eons. Anyway, they got the name Large Magellanic Cloud, and then there's a smaller version nearby. It's called the Small Magellanic Cloud, and we'll look at those a little later in more detail and figure out how they're related. But at the time, it looked like just a giant star cluster, a super star cluster, not a cluster of a few dozen or a few hundred stars like the open star clusters that we looked at in the previous chapter, and not even like the globular clusters that we're going to look at a little more closely in this chapter, that are 100,000 to 1,000,000 stars. This was hundreds of millions of stars, or perhaps even billions of stars. So So a super star cluster, but yet bright enough and big enough that you could see individual stars. It clearly was not a nearby forming solar system like we speculated these little fuzzy balls were. And she studied it, and she found that there were stars that varied in their brightness. They got brighter and dimmer and brighter and dimmer in a very regular pattern. They're so-called pulsating variable stars, as we know now. And we named them Cepheids after the first of the well-known examples in our sky. One of the brightest is Delta Cephei. It's the fourth brightest star in the constellation Cepheus. It's a star that I have my students study. It's pretty easy to take naked eye measurements and combine them together at the end of the semester and make a light curve and see that the star rises in brightness and then falls in brightness with a period of about 5 days. So she found a lot of these type of objects. They had the right color, kind of a little bit more on the yellow side compared to the sun, and the right light curves to be classified as Cepheids. What was interesting is she found that the brighter they were, the longer they took to pulsate. And the shorter they pulsated, so just a few days perhaps, then the dimmer they were. I mean, the average brightness of them was dimmer. Now, in our own sky, we can see Cepheid variables of all different distances, and so their brightness doesn't show this correlation. The special thing about the Large Magellanic Cloud is it takes up a piece of sky that's only a couple of degrees across. And if you assume that the depth of the system is similar to its width across the sky, and that's a decent assumption, we don't live in any special place in our galaxy, so there's no reason to assume that it would be anything other than roughly the same in depth. That means that within 5% or 4% or so, these stars were all at the same distance. And that's what allowed this relationship to show up. Now, she didn't know what the absolute magnitude is. Here in this diagram, we have absolute magnitudes put in. This is an old diagram, but it's not that old, 1961. We did have things figured out reasonably well by then. But it actually took quite a while before we could really figure out what the absolute magnitude of these really was. So what she knew was that there was a correlation between their apparent brightness, the little m here, and the period that they took to pulsate. So this is log base 10, so these would be Cepheids that take 100 days to pulsate. Not very many of those. 10 days, that's a lot more common, and 3 or 4 days, that's very common. Is obeyed, and you know the period, let's say this particular Cepheid in this star cluster is exactly 10 days, then you just read off from this here that it must be 3,000 times the luminosity of the sun. Then you measure its average brightness over its cycle, and you figure out from the inverse square law of luminosity how far away it must be. Sorry, I said that backwards. We know the distance to the cluster already because we can see its main sequence, so that's main sequence fitting. And then that allows us to take the average brightness of that Cepheid and realize that, oh, that's got to be, that's 3,000 times the luminosity of the sun. So it enables us to put numbers on the left axis here. And you'd like to do that, of course, for many, many Cepheids so that you can average out over the different things that could confuse you, like maybe intermediate dust between you and the clusters that can affect the brightness. So in other words, the Cepheids make excellent distance indicators. So the next big distance indicator in the distance ladder, after parallax and after main sequence fitting for star clusters, is Cepheids. What's great about Cepheids is they happen to be among the brightest stars. We looked at them in the last chapter and we saw that they're right up at the top in the red giant area. These were along the instability strip in the HR diagram. And since they're so bright, they stand out among the other stars in the galaxy. So what you do is you take a bunch of photos and you measure the changing brightness of the stars that look like they must be Cepheids. Verify from the light curve that, yep, from the color and the shape of the light curve, those have got to be Cepheids. Construct the light curve, measure the period of the pulsation, pick off the luminosity from the Cepheid period luminosity relation, and then you can calculate how far away that star must be to have the luminosity look like the apparent brightness that we see from here on Earth in our photos. So to do that correctly is a little more complex, and there's a lot more to it actually, but there's actually several types of Cepheids. There's classical Cepheids and there's type 2 Cepheids, also called W Virginis stars. Metallicity has a small effect. It's not completely negligible, and so there's some subtleties to it. But as long as you measure the brightness and luminosity in the infrared, you can beat some of these problems. Okay, so how do we know from Cepheids that our Milky Way along the sky is actually a galaxy? So it kind of happened in reverse. What we ended up doing was discovering that the nearest brightest example of a galaxy, fuzzy object, possibly, as we thought, perhaps, forming nearby star system, planetary system. But Edwin Hubble in the 1920s used the new largest telescope in the world, the 100-inch Mount Wilson telescope, and he imaged the Andromeda Galaxy carefully enough that he could actually pick out the brightest individual stars in that system, and at that point it ceased to be called the Andromeda Nebula, as it had been known, as just a big blurry ball, and became the Andromeda Galaxy. So that was when we really learned that they were galaxies. So the way he did that is he found stars that looked like Cepheids, and he looked at their brightness, and he said, my God, these things are incredibly dim. These are like 20th magnitude or something. Way, 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 way dimmer than anything you'd see in our galaxy. And he realized that this system was not something a few light years or a few dozen light years away, but it was more like 500,000 light years away, or with better measurements later and a better calibration for the Cepheids, more like 2 million light years away. There's the Andromeda Galaxy. I want you to notice the stars that are out here. These are stars in our own galaxy. The Andromeda Galaxy happens to be not that far away from the plane of our own galaxy. So we see many of our own nearby stars, and even not so nearby stars, in our own galaxy. And now I actually studied the Andromeda Galaxy when I was at UCLA doing my doctoral thesis. So I had to use planetary nebulae as dynamical probes and figure out the distribution and the dynamics of the disk of this galaxy. And also this little guy here, that's actually another galaxy. That's a so-called elliptical galaxy. We'll describe those a little later in the next chapter on galaxies in general. This is also another galaxy. It's also an elliptical galaxy. These are both little companions to the big galaxy here, the Andromeda Galaxy, which otherwise is a lot like our own Milky Way. I want you to notice the center is reddish and the disk is more bluish. And so what that's telling us is that the bluish part, the bluish stars out here, these are dominated by the light of blue giants, massive stars that are in spiral arms. See these spiral arms here. These are telling us that these are places of recent star formation. Recent star formation can include stars that are very high mass, even though they don't last very long, and they're among the most luminous of stars. The center of the galaxy is dominated by red light because star formation down here was shut off long ago, and so this is an old stellar population and dominated by the light of red giants. But we'll come back to that later when we talk about stellar populations. Okay, so you can map out, looking at Andromeda now and realizing from the Cepheids that this is actually a separate galaxy. and look at the structure of it. And so here's the basic components. There's a spherical component, sometimes called the halo out here. And then the inner halo is actually called the central bulge. Here's where the stellar density is high enough that you can literally see it as a blur of stars. Then there's individual bright clumps, which if you look at carefully you can see are actually clumps of 100,000 to 1,000,000 stars. So these are the globular clusters. There's globular clusters in our own galaxy as well, and there's globular clusters in Andromeda. And not surprisingly, their distribution is centered on the center of the galaxy as a whole. And there's fewer of them as you go out, and more of them and denser as you go in. Then there's the so-called disk, and the disk is here. That's the bluish part. And then in the center, in a vertical sense, of the disk is the reddish stuff here, and what that is interstellar gas and dust, which settles into a finer and thinner plane than does the stars, which occupy a more inflated, a thicker disk. Okay, and then there's also stars out in the halo here that are not members of globular clusters. Globular clusters are the easiest things to spot because they're just so bright. But if you're careful and you look carefully, then you can actually see individual stars out here. It's just pretty sparse. So where are we in this huge system that we call the Milky Way? Again, it's not so easy to tell because, you know, we're in the middle of it. And we're seeing it edge on. And all the dust is in our line of sight as we try and look towards the center and look towards the edge. And so we were fooled by the fact that when we look at other galaxies, we see this bright, bright, star-like almost, well, not really star-like, this bright, dense ball of stars that's so dense it is clearly the brightest part. In fact, if you look up in Andromeda with your naked eye in the fall, you'll see a big fuzzy star, and what that really is not a fuzzy star, it's the Andromeda Galaxy. And it's the collected light of maybe 100 billion stars, all in the central bulge. It's so clearly the brightest part of the galaxy, and since we don't see anything like that in our night sky, we thought that, well, maybe we actually live in the center. So in the early 20th century, we didn't appreciate the dust that hides our view, and we actually thought that we might live in the center of our galaxy. Here's globular clusters, though. These are the ones that are going to tell us where we really live. You can just tell, looking even at this photo, that these things are ancient. The brightest stars in the globular are the red giants, like that guy and that guy and that guy. This blue star here, he's a foreground star. He's not a member of that cluster. And the hotter stars, the whiter stars, are all much dimmer. So this is telling you that the main sequence turnoff point is far down into the area where the sun is, not up in the area where the blue, more massive stars are. Those massive stars have all died already, and it's only stars that are about the mass of the sun that are still on the main sequence, and even those are starting to turn off and become red giants. So when you look at them more accurately, then you can tell with your stellar models that, yeah, these globular clusters are about 13 billion years old. 12.5 to 13.5 billion years is the age that you get when you look at these. You can tell in this photo, as a comparison, you can see how much more massive a globular is than the Pleiades, which is a open star cluster. This is the brightest open cluster in our sky. It's not a particularly rich open cluster, but it's the nearest, one of the nearest. So let's look at some more globulars up close. And you can see it gets pretty darn crowded down here. In fact, we can tell you now that in the last in the last decade or so, we've got good enough technology to tell that we have black holes. Black holes of roughly 1,000 solar masses that have been built up in the action of the formation of these globular clusters. There's Here's another one. This is one of the richest ones. This is Omega Centauri. And this weird pattern here is actually a whole bunch of photos from the Hubble Space Telescope that, and then this is just a rather overcrowded picture from the ground, overexposed. But we can zoom in here and see it up close, and it's just mind-boggling how many stars there are. And also it's just so obvious that it's the red giants whose light dominates these clusters. So these globular clusters look kind of orangish reddish. And the main sequence stars, these are stars that are only about as massive as the sun or a little less. Lots of those too. So here's the thing. Hubble found globular clusters in Andromeda as well. And they're roughly spherically distributed and centered on the center of the galaxy. But we had known in our own sky since the days of William Herschel, who mapped out where the globular clusters were in our night sky. And any star chart and any amateur astronomer will tell you that globular clusters are strongly concentrated in the summer sky and strongly concentrated in the constellations of Scorpio, Sagittarius, Ophiuchus, Centaurus. Those are the constellations that are closest to the center of the brightest part of our Milky Way as it bands the whole sky. That must be the center. So that was the clue. The center of our galaxy is not where we are. It's off in the direction of Scorpio, Sagittarius. Can't get damped out for stars. Vertical motion can get damped out for gas and dust, but not for stars. They're too dense, and they just don't feel any air friction with the very, very low density interstellar medium. So why was it so hard to locate ourselves within the Milky Way? Dust. We just didn't appreciate the dust. So let's take a look again. Here's a visible light picture. The center of our galaxy is right about here. Right about there. And this is Antares, and this is the head of Scorpio, and so this is near the tail of Scorpio. Here's Sagittarius, the teapot, bright stars in the summer sky. And the center of our galaxy is kind of on the border between those two constellations. But there's all this dust here. That's what all the blackness is. And we can't see the center. Now, I, for one, am very glad of that, because I can see how brilliant is the central bulge of most galaxies. In fact, it's said that if we could see the central bulge of our galaxy, it would be about as bright as the full moon. So I don't really want something as bright as the full moon sitting right here, because there are so many neat objects to look at in the summer sky, like Messier 8 here, and these, the Omega Nebula, and Eagle Nebula, and there's a whole bunch of great nebulas and star clusters and dark nebulae like the Horse Nebula right here. Looks kind of like Bucephalus from Alexander the Great stories. And I don't want all that permanently obliterated by a permanent full moon of light that never, ever, ever goes away. I mean, I can put up with a full moon once a month, but permanently, that would be a bummer. It did make studying the center of our galaxy a little harder, but we figured out ways, so we'll come to that a little later. How old is our Milky Way? So the globular clusters, again, hold stars more massive than the sun, have all evolved off the main sequence. So what are these guys doing here? So these are former binary stars, two stars going around each other in a tight binary. And as binary stars, they each had a mass less than the mass that they have now, because now those two stars have actually merged together. They've radiated enough of their energy, mostly through gravitational radiation, that they have merged together, and now they've become a single star. And that single star is more massive than you would expect a star of that mass to still be alive in this cluster. So basically they spent most of their life as low-mass stars, which therefore evolve slowly, and only recently have they become higher-mass single stars, and that's why they're out of place here. But these two are also going to evolve off and become red giants. So there's our galaxy, and there's the central bulge, and there's the dust. So that's what I wanted to show you. The dust plane is thinner than is the stellar disk. The stellar disk is thicker, as we just talked about. So 25,000 to 28,000 light years. I've seen different figures all in that range. Depends on what study. It's a little difficult to try and get it perfect. So, but you know, we got it pretty close. 26,000 light years away. Center of our galaxy. Let's look at just our immediate solar neighborhood. So this is a little hard to see. I got this actually from Sky and Telescope many years ago. But it is a really good way of seeing what we call the local bubble. So we are like the boy in the bubble. We live in a bubble. And the sun is right down here. A little hard to see, but there it is. And mostly there's not much around us, but if you look in a vertical sense, you can see a little bit of interstellar gas here. Mostly the interstellar gas is piled up in this region here that's many light years away. You know, I don't know, 100 light years away or something. So the local bubble, what is that about? Fairly recently, just 4 years ago, Wallner and then Breitschwert et al., they did some really nice studies of looking at ocean sediments and discovering iron-60, heavy isotope of iron, in the sediments. And iron-60 is only produced in supernovae and has a half-life of only about 2.6 million years. So what was interesting is they found layers. A layer of this iron-60 rich material, 1.5 million years old, and another 2.3 million years old. So it indicates that there was 2 supernova blasts that happened at these times, and they were relatively close. I mean, compared to 30,000 light years away to the center, these are only 300 light years away. So this is only one. Both of these supernovae were only 1/100th of the distance to the center of the galaxy, and they agree pretty well from the kind of blast wave you'd expect from that, with the local bubble size and expansion. So we think that's probably what happened. This is just a beautiful photo. I've tried to reproduce a photo like this with my own equipment, but I've so far failed. The sensitivity required is very high. These colors look gorgeous here, but you need really, really pitch black skies to try and get down to sky brightnesses that will allow you to see this. So this bright star here is Antares. This is a red supergiant. This star here is Delta Scorpii, or rather, I think this is actually, yeah, this is Delta Scorpii. And it is very hot. This star is very cool. It's only about 3,000 degrees, 2,500 degrees. This star is very hot, maybe 30,000 degrees, and it's ionizing the hydrogen around it to give you this nice, sharp fire engine red color. The orange color you see here is really just light reflecting off of dust. It's the red light of Antares reflecting off of rather large dust grains. There's also dust surrounding Rho Ophiuchus, which is this star here, smaller dust which will scatter blue light. And also Rho Ophiuchi is a much hotter star. It doesn't give off much red light. So mostly you see blue light. And there's another example of that up here. And then there's M4. That's a globular star cluster. And here's another globular cluster. So close to one of the brightest stars in the sky. The head event of Scorpio is actually a pretty neat place to explore in summer skies. So there's the local bubble, and there's the sun. So the local bubble kind of encloses all this. And we are on the inside edge of the Orion spiral arm, or what's sometimes called the Orion spur. It's a short segment of spiral arm. The next spiral arm, closer to the center of the galaxy than us, is the Sagittarius spiral arm. And that's right here. And there's some associations there. The Scorpius-Centaurus Association, that's an old star cluster, open cluster. And here's another map showing our galaxy. Putting together a map like this is actually very, very difficult because we can't see our galaxy from the vantage point that we show in this image. The sun is right there on the inside edge of the Orion arm, or what they call the local arm here. The next nearest spiral arm to the center is the Sagittarius arm. Then there's the Scutum Crux arm, and then there's the 3 kiloparsec arm, and then there's the center in here. And one thing really interesting that we didn't know until the 1990s, which I still think of as pretty recent, is that we don't live in an ordinary spiral galaxy like the Andromeda Galaxy. We live in a barred spiral. And the bar is obvious in this drawing here. It's a short stubby bar. It doesn't extend out anywhere near as far as the sun. And so it actually took pretty good mapping of distances and velocities for certain red giant stars in order to be able to map out this short piece of straight spiral arm, which we call a bar. So we live in a barred spiral. We'll talk about galaxy types in the next chapter. But we've already introduced spiral arms. What are spiral arms? That's the next question. Spiral arms are places. They are spiral density waves which sweep through the gas and the dust. They compress it, and being higher density aids star formation, and the star formation makes new stars. Some of those new stars are massive. The massive stars are very, very brilliant, and so those are what show off the spiral arm. Now, by the time the spiral density wave is moved over to here, those massive stars, we remember from our last chapter, they only last a few million years. And one thing I didn't mention, but I will emphasize now, the sun takes 250 million years to go around the galaxy once. So stars that live only a few million years, they don't even get to be 1 year old. They die in infancy. And by the time the spiral density wave, is moved on to here, then these stars here have already died. They've already blown up and become supernovae, and they're gone. And now the stars you see are here. And basically it's because the lifetime of stars that are massive enough to really dominate the light of a spiral arm, the fact that the lifetime of those stars is very short compared to one orbital period around our galaxy, that's why spiral arms are so clearly evident. It's because they're narrow, and they're narrow because the amount of time that those stars are alive and therefore show off is short. Okay, so this now is a drawing. This is not a real photo of any kind, but it's trying to show the distribution of a stream. So our galaxy is a big, massive galaxy. We live around a pretty average, ordinary star, but we don't live in an ordinary galaxy. We live in a rather extraordinarily large galaxy. We live in a pretty beefy, big galaxy. And what you're seeing here is a small galaxy that has fallen in. And as it falls in and orbits around, it's getting pulled apart. So it's getting stretched into a noodle. So remember the tidal force. Things that are gravitating towards other things, the near side is pulled more than the far side. So there's this secondary effect of being stretched while you fall in. And if you're as loosely bound as small galaxies are, then it's pretty easy to actually pull them totally apart, almost like the way you make cotton candy in a carnival. Now this is an actual set of photos, and then rendered with with colors and so forth to make a map. But these are actually photos that have been reassembled. And the most obvious thing here is the galactic plane. This is the plane of our galaxy. This is an all-sky image. So this place here is the same as this place over here. And what I wanted you to notice is the Magellanic stream. There's the large Magellanic Cloud. That's a galaxy. There's the small Magellanic Cloud. It's a piece of the same galaxy. Here is more stars in blue. And there's little bits and pieces of stars, clusters and things, and globular clusters that you can see along this whole stream. So this is now called the Magellanic stream. And clearly it is a single larger galaxy that got pulled apart as it fell in too close to the Milky Way. And the star systems are still visible, but at some point they'll probably fall in far enough to just merge with the stars in our own galaxy. This is low-metallicity gas from far away falling into the Milky Way. So you see streams in several places here, and these streams are tidally distorted intergalactic gas and dust, and even in some cases stars, like here and here. So that's what happens is low mass galaxies tend to aggregate and be formed in the neighborhood of big massive galaxies, and so we've got our whole little fan club of little teeny galaxies that follow us around. Okay, so now let's take a trip to the center of our galaxy and see what we see. So in visible light, mostly you see dust. You can't really see the center of our galaxy. Again, it's right in here. Now, if you look along this area, though, you can see a little bit of the central bulge of our galaxy. In this area, I think it's this area, that's called Bada's window, a place where you can see down close but not at the center of our galaxy without too much dust obscuring your view. Now, this is an infrared picture, and an infrared picture is going to show stars and the plane of our galaxy, and now you see the dust as well. That's the darkish stuff, but it's nowhere near as obvious as it was in visible light. This is part of the 2-mass survey. 2 micron is what that stands for. 2 microns is about 4 times the wavelength of the visible light, and that's rather long, and you're really going to be dominated by infrared light now from a cooler stellar population, and you're going to be able to see through dust much better. So there's the large Magellanic Cloud, and there's the small Magellanic Cloud, and you don't really see the stream that goes with it because that's something you would more see with radio telescopes. The hydrogen gas gives off radiation that you can see. Another image, another infrared image, and now the large Magellanic Cloud and the small Magellanic Cloud are more obvious. The light that you're seeing here is red light, and there's a globular cluster right next to the small Magellanic Cloud, and in fact most of these little teeny globby things that you can see in the photo here, these are globular star clusters. They are dominated by red giants. Red giants are cool enough that they give off a fair amount of infrared light, and they're pretty concentrated, so they're kind of obvious. Okay, and now we're combining 2-mass data and also the MSX, which is a mission that looked at even longer wavelengths. And now you can see something's going on down there in the center of our galaxy. It's not, you don't really see the dust so much anymore. You're able to look through it. So let's do that again. The galactic center's right there. And now we zoom in. And this is an image taken in longer wavelengths, long enough to show these rings here are made by stellar explosions, we think. Supernovae that have gone off. So there's active star formation going on not too far from the center of our galaxy. And then if you look in towards the very, very center here, we're going to take that and blow it up a little more. And it looks like this. And it looks like this. And when you see that, you should probably get a bit of a flashback and say, oh, that kind of looks like those prominences around the sun. And yeah, they're actually closely related. It's the same physical thing going on that dominates the light here. What this is radio, well, in this case it's radio light, but it's dominated by, well, let's say the structure's shape is dominated by the magnetic field, just like on the sun. So magnetic fields near the sun channel the gas near the sun and constrains them to follow along the field lines. And the same thing must be going on here. So anybody who's looked at enough magnetic field dominated photos could look at this and just say, oh, this is too obvious. These are magnetic fields that are channeling this stuff to only follow along the field lines. Why would that be? And why would there be radio radiation coming along these magnetic field lines? And then you realize that, well, if you have high-speed electrons, those electrons would be spiraling around the field lines, and that's a form of accelerated motion that would give off light. In this case, very long wavelength radio light. Well, why is there free electrons here? I mean, don't electrons like to find protons and be together and be neutral hydrogen? Yeah, usually. So that's a giveaway that something is powering this down here enough to send out enough ionizing radiation, not seen in radio here, that is actually ionizing this gas. So it's knocking the electrons and the protons of normal hydrogen and knocking them apart. Here's another image, and now we're zooming in to just an inner 30 or 40 arc seconds. So this is like 1 arc minute across here. That's only about the size of a big crater on the moon in terms of angle. And it looks like you're seeing a spiral. Like stuff might be spiraling into the center of our galaxy, which is right there. And then a better image shows, yeah. So these arms are not spiral density waves like we talked about before. This looks like material that's actually going in to Sagittarius A, the strongest radio source in the sky. So there's very strong radio radiation coming out here. That's telling us there's a lot of free electrons that are spiraling pretty viciously around the magnetic field line. So why is there such a strong magnetic field? And where's all the energy coming from to ionize all this gas? That's the question that you'd normally ask once you see this. So the next clue, there's Sagittarius A in infrared light. So the next clue came from UCLA astronomers. Remember, I got my PhD at UCLA, so some of these people I knew. Andrea Ghez and her group, and this is now 20 years old, and what they did is they took very careful photos with the Hubble Space Telescope, and they showed that there are stars there that are following orbits like this. So the stars were moving fast enough that you could literally see them undergoing proper motion. So 1995 to 2002, so here's 7 years worth of orbital motion. Remember now, this is like 28,000 light years away. And this is like half a degree. So to have these stars move that fast, did I say a degree? I think that's an arc second. I'm sorry. Arc second. So you need the Hubble Space Telescope to see down to that kind of angular view. Because because this square here is this whole picture here. Look at this guy. Look at the orbit that this SO16 follows. Deep plunging orbit all the way into there and then zooms right back out. This is telling us that the mass around which these guys are orbiting is a very concentrated mass. And when you use Kepler's laws and you look at how fast they're moving, and when we know how far away the center is, so that gives us the other orbital parameter, and you calculate and you find out that, my God, the mass that's swinging these stars around is like 10 million times the mass of the sun. And yet, you can't have stars that are anywhere remotely close to that kind of mass. Stars bigger than about 150 solar masses will actually have so much luminosity they'll literally blow their outer envelope off immediately. They can't be contained. Their Eddington limit has been exceeded, and you won't have stars that last at all for masses like that. In fact, the only way to have that much mass in that tiny a volume is for it to be a black hole. So this was really nailing the case that we have a giant black hole in the center of our galaxy. We'll do the whole active galaxies and black holes story next week, but and so it's not at all surprising we have a black hole in the center, but it was only an inferred probability until this work, which really cinched the case. So how did the Milky Way form? That's really more properly a subject for cosmology, because all galaxies, especially all big galaxies, formed right after the Big Bang. And so I'm going to save most of that for later. But just very briefly, protogalactic clumps, or smaller galaxies, where star formation had already begun, fell together, or to use the technical term, smushed together, and became the central bulge of our galaxy. And then more slowly and gradually, gas, intergalactic gas fell in, hydrogen gas, fell in from farther out. It fell in with some angular momentum because it was also feeling the pull of, for example, the Andromeda Galaxy. So it didn't fall straight in, it fell in with some sideways motion, and that's why it settled into a disk rather than just falling straight to the center. Okay, and then globular clusters formed during the proto-galaxy stage when collisions of fairly big clumps of pre-existing stuff was happening. That's the kind of environment we need in order to make globular clusters. And all this happened easily within 1 billion years or so after the Big Bang. It's the same for most other galaxies. So the evidence for the formation sequence of our galaxy comes from work done by Walter Baade in the 1950s. So he discovered something really interesting. Stars with so-called metals, remember astronomers use this loose term called metals to mean anything that's heavier than helium, were all in the disk. So those stars were called stars of population 1. Stars with high metallicity were called population 1. Stars he found, there were also stars he found that had no metals. Those he called population 2. So to divide the stars between those that had metals and those that didn't wasn't particularly informative, and calling them Pop 1 and Pop 2 wasn't particularly informative. What was informative was where these stars are found. So I already hinted at it when we looked at the Andromeda Galaxy, but the big clue is that the Pop 1 stars, the population 1 stars, the ones with metals, they're all found in the disk. You don't find any of them out in the halo. The Pop 2 stars, they're all, well, most of them, the large majority of them, are in the halo, in the central bulge, in the globular clusters. They do not dominate the disk. So the story that emerges is that the bulge formed first out of pristine material, fresh from the Big Bang, and thus had only the elements, the chemical elements that emerged from the Big Bang, and we'll justify later why that's only hydrogen and helium. Lithium, beryllium, boron, carbon, oxygen, nitrogen, sulfur, etc., all the way to uranium. All of those are only formed later inside stars. Out of the Big Bang came just two elements, hydrogen and helium. So, age dating about 70,000 red giants across our galaxy confirms this general picture. In the video link, you'll notice how there's more stars, core stars in the central bulge, and they make up the very old stars which form first, then the flattened disk above and then below, and then we call those the intermediate age disk, and the youngest stars are the closest to the center plane of the galaxy. So there's that. Extreme Popl are stars that are very, very tightly fit on a flat plane. And of course there's a gradation here between. They're not really that distinct from each other. It's a whole distribution. All right. Well, that takes us to the end of our Milky Way chapter. So what we're going to do next week is we're going to talk about galaxies in more generality. So now we've studied a spiral galaxy up close and seen the interstellar medium, and we have a hint now about how galaxies evolve. The central bulge forms first out of clumps of gas and stars that existed right after the Big Bang, stuff that formed early. And the stars, of course, that are in that early stuff are already so tiny and so dense that when they collide together, the stars themselves literally don't collide. It's only the boundaries of the system that overlap, and the stars themselves are just far too tiny to do that. And then that makes the central bulge, which is now made of old stars, stars that date back 13 billion years or more. And the disk only forms later, and then as the disk gets more and more settled by gravity, gradually it gets dense enough that you can have star formation going on in it. But even there, it's tough, and what really helps star formation to happen in the disk is these spiral density waves. Now, I didn't really explain what a spiral density wave is, but the orbits of the stars in our galaxy are not perfect circles. They are not very elliptical, but they have some ellipticity, and we remember one of the properties of ellipses is that the stars will, the orbits, the things in the orbits will move more slowly when they're far away, and they'll move quicker when they're in close. So what that means is that the stars will slow down and tend to congregate, and there'll be a bit of a traffic jam, a bit of a traffic jam in the outer parts of these orbits. And when those resonate with each other and form a larger concentration, I guess I'd say, then we have the ability for the gravity there to pull stuff together and make stars. So star formation is enhanced by these spiral density waves. All right, well, I'm going to end it here. So that's almost an hour, and that's most of our hour-and-a-half class. So what I'll do is I want you to listen to this tomorrow, play it on YouTube. I'm going to try and get it uploaded to YouTube before class starts tomorrow at 9:30. And so from 9:30 to 10:30 or so, I want you to be watching this lecture and watching the slides, and then for the last half hour of the class, and then we'll get together on Canvas and you can ask me questions. All right.